Hey, how are you?
Good. Tired, but good.
Gotcha. Okay. So you wanted to go over some optics today, right?
Yes.
All right, let's do that. Um, okay. So let's see. So okay, so why don't we start with, I guess, um, like images that can form from lenses and what type of images can form. So here, I'll write optics. You said something about mirrors, lenses. Okay. So let's think about the different types. Well, okay. So for a, let's see. Okay, so what can you tell me about optics, I guess? Like tell me like what you know, what you feel comfortable with, what you feel uncomfortable with. Go like that.
I can start with the most uncomfortable. I think it's easier.
Yep.
Um, I would say that sometimes like when I like converging and diverging, sort of like when I see like where the object is, where the image is, focal point, and like sometimes they're negative and sometimes they're positive,
Okay.
and like knowing which is which for which one, I
Mm-hmm.
would say. Um, yeah. It's like I guess very basic things. Uh yeah.
So got it. Okay. So let me so generally speaking, say we have that, that. Actually, let me do this. Okay, so let's say that the middle here is the lens. Let's see. And the middle here, let's say, is the mirror. So what a positive number will be what's to the, well, I guess this is the same actually for both lenses and mirrors, so I didn't have to draw separate ones, but if it's going if it's upwards like this, or if it's to the right of the optical device, these will be positive values. Yeah, I'll just use one. Or actually, you know what? I'll leave it like this because I'll draw some pictures. But same thing, positive. Oh, this is too close, so it looks like it's the bottom. So I'll move that. So I'll put it to the side maybe. So yeah, positive. Oops. And if it's to the left or down, it will be negative. So what I mean essentially then would be, so let me draw like something like that. And let's see. Like that. So for the lenses, right, we have which one is the, so what I drew, from what I drew, which one is the convex shape and which is the concave shape?
I think the bottom one is the concave,
Yep.
right? And
So
the top is convex.
yep. So you could think of like the word cave as being like an opening. I mean, that's also why a cavity is called a cavity. It's an opening, right? So concave will be thinner at the middle of the lens. So okay, and convex will be thicker at the middle of it. So and typically when you have these, you'll have a focal point, and what a focal point kind of is if you have, I can get a picture. So I'll put this like here. So you can see that. So in this, you can see the image that I pasted in, right? So for a concave lens here, right? So the light that hits it from the left, like, is parallel to the ground, I guess, or yeah, the ground. And it hits the convex lens, and the light rays start to converge, and that point at which they converge, like the distance between the lens and the point at which it converges, is the focal length. And then you can see for a concave lens, it's similar in that the light hitting it from the left is parallel, it's to the ground. Don't worry about this dotted line stuff yet. It's just parallel to the ground, and it touches the lens, and this is going to cause divergence. So the light rays move like away from each other. But from like the divergence, if you trace it back to where it converges, that's what these dotted lines are. The place at which it converges, right? The distance from that to the lens is the focal length.
Okay.
Yeah. And so, yeah, so that's going to, so, and you can also see then that, like, this kind of convention, like, we see here the focal point is to the right of the optical device, which means it'll be a positive. So you see a positive sign for the focal point. And if it's to the left, like it is here in the concave, it'll be a negative focal length. So that's what a focal point is, because sometimes you'll get questions that that will ask you what's the focal point, like when it's not given and without the formula being able to help you. So this can just help you conceptually see what a focal point is, a focal length.
Yes.
Yeah. Now, uh, so okay, now I should talk about, so these are spherical lenses, and I'll tell you what that, like why. Whoops. Okay. Like, so imagine two like circles overlapping like this, right? So when you have that, this is your convex shape, right? And if you have them like this, then this is your concave, right? Your concave shape.
Yes.
So what we call concave and convex optical devices, they're called spherical because they're based on spherical like circles, right? So that also means that the that there's a radius like that, let's say r, that can be considered the radius of curvature. And so something so the radius of curvature, let's see if I can find a picture. Okay, so here we have, oh wait, I was wanted to show something else. So, hey, okay, um, so there's going to be a value called, well, you'll have, so the radius of curvature is going to be equal to 2f, radius of curvature. So, um, so you know that would, for like this, it would be like over here, like 2f. Oh wait, sorry. It will be here. 2f, radius of curvature. So, okay, so if we go back to this here, so typically what you'll see will be something that's going to be like a focal length. And you'll also see something that will be like at 2f, which is the radius of curvature. Now, if we draw these out, oh wait, I'm trying to find the image that I just had. Oh, okay, okay, got it. Okay, so yeah, f and 2f. So let's say we have an image that, or let's start with, okay, let's say that we have an image like, let me move this a little bit. Let's say this is 2f, and let's say that we have an image that's upright. That will be a positive sign for the image. And since it's to the left of the lens here, we would say that, okay, so I should first say that when it comes to um okay, when it comes to optics, you're going to have a formula that's like 1 over focal length is equal to 1 over object distance plus 1 over image distance. And so so like left to right, like left to right is going to be like an object distance or an image distance. So, that's what's meant by that. Um, but the other one would be so magnification is negative image distance over object distance. So what that means is that if you have, well, if your object uh is upright, that will be positive. If it's, upside down, it'll be negative. So that's just what those conventions mean. So if we go back to this,
Um,
yeah.
you're referring to magnification. Like if it's upright, it will be a positive magnification.
Oh yeah, yeah. So magnification just kind of brings it together in terms of the image distance and the object distance. I just included that because it's another formula. But yeah, for objects, if they are upright, our convention is that we refer to that as positive, as a positive number. And if it's inverted, we say that it's negative. So for this image here, it's a positive image in the sense that it's upright, but it's to the left of the lens, so its object distance will be negative. Okay, so
Okay.
yeah, so yeah, so that's an example of that. And then I could say for let's make it green or whatever, something like this, that will be negative, right? And that's going to be true for the mirror as well. But when it comes to so wait, maybe I should just do, so when it comes to the mirror, uh, since a mirror does not involve, since a lens involves light going through it and coming out the other side, right? It makes sense to draw lenses completely, like the convex one is a complete, shape. The diverging one, concave one, is a complete shape. But for mirrors, we only need to concern ourselves with the leftmost part of that shape. So what I mean by that is that you can have, um, so if it's convex, it will just be like this. Okay. And if it's concave, it'll just be like that. And um and then you can kind of see how it would reflect stuff uh based on that shape. So like let's say we have some image here, or rather I could just kind of draw it in terms of um the light rays. So like for instance, it would bounce off like this, right? Um,
Yeah.
Whereas here it will bounce off like that.
Yeah.
So that means that for a convex mirror, it will be diverging, right?
Yes.
And a concave mirror will be converging, right? And For lenses, the convex lens will be converging, and the concave lens will be diverging. Okay. So okay, we got the sign convention stuff there. So now let's talk about, yeah, let's talk about images. So for diverging, which would either be a convex, oh, oops, yeah, convex mirror or concave lens, this will always produce SUV, and that means small, upright, virtual image. Now, what how can you tell if something is a real image or a virtual image?
Whether it's like upright or inverted.
Uh, well, aside from that, I guess, right? Like what in actuality in real life, right?
Is it like when like if you actually have like the focal point, like the rays converging? Like if you actually have a focal point, where the image is created?
So I guess you're telling me like what it would be based on like those terms, but just, in terms of like real life. In real life, what's the difference between a real image and a virtual image? So, have you ever used like a magnifying glass to like burn things when you're a kid?
No, but I've seen it in cartoons.
Yes, yes, exactly. So, do you think that's so okay, let's think about that, right? So, let's say we have a magnifying glass here, right? So, okay, so you what so when you see it in like cartoons and stuff, you would see that like it would be kind of like converging at a tiny kind of point. So okay, a real image is something that can be projected, and not just projected, but its projected image could be treated as an object for another lens. So let me start off with the example with a magnifying glass. So when you burn something with a magnifying glass, the image is the sun. Okay. So the light rays from the sun come together, right? And they hit the magnifying glass, which causes the rays to converge. And then it produces, so this is the object. It produces this real image that can be projected. And you know that it's being projected because you would be able to see it like a kind of small, kind of like yellow kind of color thing. Um, and if it's burning things, right, it's definitely a real image because it's causing like the light rays to settle on a single point and raising the temperature of that, right? So a real image is something that can be projected. It can be projected and also could be considered an object for, let's say, another lens. So like when you watch something in a movie theater, right? You're watching a real image from the projector. Okay.
Okay.
Now, if that's what a real image is, a virtual image cannot be projected. Okay. Because which means then a virtual image cannot be used as an object for another lens. So you can't, burn things like that. And that would be like what you see in a mirror. Like, let's say this is a flat mirror, and, let's say this is you, and this is the reflection. This reflection is a virtual image because you can't project it. You can't do anything with it. It exists in theory. Okay. So, yeah. So a real image is something that can be projected, whereas a virtual image cannot be projected, and you can't really have any evidence that it would exist, but let's say that we took like a laser light and we like shined a laser light on the mirror. Like, sure, you would get the reflection of the laser light thing, but the laser light can be bouncing off of the mirror and hit some other point. And if that other point can be like a new point, like it would be like projecting it. So you can have a real image in that regard. Okay. But if it's like as if it's with it, because like if you're like 1 foot away from a mirror, it's as if your well, it's not as if, it's actuality. Your virtual image is as if it's 1 foot inwards into the mirror. Okay. So yeah, so real virtual. So yes, so if it's diverging, it will always be small upright virtual. Okay. But if it's converging, which means it'll be a concave mirror or a convex lens, the type of image depends on object distance. Okay. So
Okay.
So yeah, let's go into that. So let's say that we have, so I'll start like something like this, and I'll make this the lens, and then I'll make, let's say this is F, this is 2F, and I'll even go F on the other side and 2F on the other side. So, and let's maybe create like let's say like a little kind of like a box with um so here, oh, okay, so here I'm gonna write object distance, here image distance, and then here type of image. So let's start off with, and it corresponds to this over here. So let's start off with actually, let's start off with, let me do this. Okay, let's start off with, let's say this, damn it. Let's say this point here is infinity, okay? Like infinite distance. And, let's say at infinity, we have this upright image here, right? So when this happens, okay, so I'm going to start filling out this table, and we can kind of go into like how to know in the diagram above, but I'll start off with just the table. So if the object distance is at infinity, okay, it will create an image distance that is at the focal point. Okay. Now, what you'll see, okay, let me say something like this also. Um, so here I'll write, let's see. Okay, so okay, so um okay, so typically you will see real images inverted and virtual images upright. Now, there's one exception here, and it has to do with like this. So like I know I said small, like upright, virtual, right? But it would be more accurate for me to say, like, think of upright as a verb. So, I mean, I can't say uprighting, but that's just to show you that it's like a verb, because what you can have happen, right? You can have something like this happen. You can have, let's say, like, let's say we had something like this. Let's say you start off with an object that is upside down, right? Then it will be uprighting that, or to make, it upright. So it depends on what you have like initially. So the inverted and the upright, think more so in as verbs, but yeah, I'll go into that more in a sec. So okay, so we're gonna have um so at infinity, object distance, image distance will be at the focal length. Um, and the type of image that you would get will be a very tiny, right, inverted real image. Okay. And 1 over f is equal to 1 over object distance plus 1 over image distance. If the object distance is infinity, 1 over infinity basically turns into 0. Because if you imagine 1 divided by a number, as if you divide it by a number that gets really, really big, it will make that overall number really, really small, right? So if added, so like 1 over infinity turns into just 0. So you just get 1 over f is equal to 1 over I. So the image distance will be at the focal length. And yeah, and it'll be a tiny inverted real image. So this is a good example of that. The sun we can treat as the object, and we can treat that object distance as infinity. Like it's really like whatever. I think it's like 93 million miles or something. But if we're thinking about focal length and stuff in the centimeter realm, it's pretty much at infinity, right? And it makes a real image that's extremely tiny. And if you remember about intensity, like intensity is inversely proportional to the area. So as the area gets smaller, the intensity gets larger, which is why making this really tiny real image would have high enough intensity to burn like leaves and stuff, right?
Yep.
Okay, so yeah, so that will make a tiny, tiny image. So I'll kind of like it's at the focal length, but I already wrote an F here. Maybe I can write the F up top. But yeah, you'll get a very tiny inverted real image over here. Okay. All right. Now, yeah. So, all right. Now let's consider if the object distance is further than 2f, but not at infinity. You will end up with an image that will be between f and 2f. Okay. And what type of image this will be small inverted real. So SIR, small inverted real. Okay. So that would be like, so if I had something like this, so that's object distance beyond 2f, image would be between f and 2f and small, but not as small as like what's tiny, right? I'm gonna make these images larger just to make it more exaggerated. Oops. Okay. All right. Then let's consider the object at 2f. At 2f. So when the object is at 2f, the image will be at 2f as well. Okay. And the size will not change because if we go back to this, image distance and object distance at 2f are equal. So this magnification term is just 1. So this will be SSIR, SS meaning same size.
Okay.
So I'll draw that in blue here. So at 2f, you have that. And at 2f, I still have that above. So below. So let me put it above. Yeah, you will get same size, inverted real image. Okay. All right. Next, let's consider the object between 2f and f. So f object 2f. Now this will create an object distance. Oh, sorry, we'll create an image distance beyond 2f.
I
And
see.
now you might be able to see a pattern here. So,
Yeah.
Good. And now we also have the image distance being larger than the object distance. And if the magnification is essentially image over object, like image distance over object distance, we should now have a larger than 1 value for that. So now this is going to be LIR. What do you think that would mean?
Like large inverted real.
So I'll do that with green here. So if we have something that's like here, let's say, it will produce an image that will be further than the 2f and larger and inverted. Okay. All right. Now, what do you think the next one would be?
Like at the focal point.
Very good. And where do you think the image would be?
There's something about like at the focal point there being no image, right? Or I'm
So
confusing.
let's just see what we can get from this pattern, right?
Okay.
So what would the image distance be here?
Farther than uh farther than the green one. to like more to the right.
So the pattern, right, we talked about. So what I meant by the pattern, right, is that, so you see how when object is between f and 2f, image is
Mhm.
greater than 2f.
Yeah.
And you see when object is greater than 2f, image is between f and 2f, right?
Yeah.
So so now if object is at f, when the image was at f, what was object distance?
When the image was at f, what was, could you repeat that?
Yeah, what was the object distance?
Um, at f, infinity.
Infinity, right?
Okay.
Now we have the object is at f. What do you think the image distance will be?
It's infinity.
Yep. And yeah, if it's at infinity, you can't see it, right? So we say no image.
I see.
Good. Now we can have an additional one here, which can now be what if the object is within the focal point? So now this one is new. So what will happen is you will have the image at greater than 2f, but on the opposite side. So what that means, whoops, let me make it so it's more like greater than. So what that means is that this will produce, so okay, I should say opposite side, right? What does that mean, right? Because that could be confusing. It'll be the opposite side of what you've been doing so far. So far for the image, we've been making the image to the right of the optical of the lens. So now it'll be greater than 2f on the left of the lens.
I see.
Okay. So 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 this would be large upright virtual image. So I'll use orange for that. So let's say we had our image here. It will then produce a larger upright virtual image at a point greater than 2f on the left side now. So something like that,
Okay.
right? So so if we kind of look at, oh man, all right. So if we kind of look at this together, what we can observe, right, is as the object as the object gets closer to the lens, meaning as the object distance decreases, the image distance increases, right?
Yeah.
And since we also know that magnification is essentially the image distance over the object distance, as the image distance increases and as the object distance decreases, magnification increases, right?
Yes.
So that's the pattern. And this table, I have in the PDFs folder like an optics table that I would just kind of memorize. I mean, you also see it conceptually, but I'm not, and I don't think anyone really wants to do, like, I obviously love physics, but geometric optics is truly annoying. So I don't think anyone wants to draw ray diagrams like what I drew right now, like this isn't even really a ray diagram. A ray diagram is when you do like, something
Yeah.
that goes there, something that goes in the center. No one wants to do that, not even me. So the table, I would say to like memorize it, but also you see like the patterns involved, and all of that stuff.
Yeah.
So let's see. Let Okay, so let's see if we can, or do you have like any of those optics kind of questions from like UWorld or something?
I did do an optics passage.
Mm-hmm.
I can pull up.
Oh, and I guess I'll just go over one more thing real quick. So, um, do you wear like contacts?
Yeah.
Okay. You're nearsighted, I'm guessing.
Yes.
Okay. So, um, okay. Now, a regular eyeball is around 2 centimeters in depth. Greater than 2 centimeters here, less than 2 centimeters here. So I'm nearsighted too. And what that means is that our eyeballs are longer than normal. So what does that mean? That means that when light rays come in, so our cornea is a converging lens. So when light hits our cornea and goes past, it starts to converge. And we want it to converge at the retina. And that's at the back of the eyeball, right? So if your eyeball's too long, they converge in front of the retina, right? So what you do is you wear glasses, and now the type of glasses that you wear would be a diverging lens. And you can kind of like, I mean, it's you can't really do it with contact, but like with my glasses, I can kind of feel it, and I kind of feel like the center of it being thinner than the
Mm.
ends. So what that does is it the light rays that come in, it converges a bit. I'm sorry, diverges a bit until it hits the cornea, at which they'll converge again, but it'll delay it so that it converges further back. And it'll just be the right amount for it to converge at the retina. So that's what our glasses do. Now, yep. Now, for people who are farsighted, their eyeballs are shorter. So when light hits and starts to converge, they will converge behind the retina. So what type of glasses do you think these people would wear?
Um, converging.
Mm-hmm. Like that. Because then when you do this, they'll start to converge sooner. And then when they go through the retina, they'll converge at the, well, like uh they'll converge like sooner. So it'll be at the retina. So yeah, so that's for so this is normal. This is myopia, which is nearsighted. This is hyperopia, which is farsighted. Now, that's different from like, when people age, they start to need glasses. And, like I don't know if but like, at like CVS and Duane Reade and those types of drugstores, they sell glasses that all
Mhm.
have, so like, your prescription's a negative
Yeah.
number, right? Um, but those will be positive numbers. Um, those so okay, the hyperopia thing, which is farsightedness, that's how it is like this. But some when people get older, they start to need glasses, and it's not like their eyeballs as they get older, like change size. So what really happens with people as they get older is we have something called a ciliary muscle uh, that helps us accommodate. Like if we look at something close and then we look something far away, the ciliary muscle helps our iris like kind of like open and close a little bit. So as people get older, that muscle kind of weakens. So people then end up needing converging lens glasses because kind of to help them with seeing far away. But yeah, so this is lenses applied to like a real life thing, like glasses and stuff. So
That's helpful.
yep. So okay. Yeah, if you can bring up some questions, I can like kind of well okay, maybe I'll just have you do this. I'll call this like optics, and you can export this, and then we can go and then you can share a screen and we can
Okay.
do like the questions like that. I was gonna say this, or I could paste the questions directly on this, but I think it'll probably be faster for you to
Yeah.
like, share it. Yeah.
Okay.
Oh wait.
Um,
Oh, I was gonna add something, but
I can export it again.
yeah.
It's
Okay.
fine.
Let me add something. Okay. Um okay. Magnification negative I over O, which means essentially it's proportional to image distance, inversely proportional to object distance. All right, now let's talk about certain magnification values. If your magnification value is greater than 0, aka positive, the image that it will produce will be upright and virtual. If the magnification is negative, it will be inverted real. Okay. And
Okay.
if the magnification is larger than 1, it will be a larger image. If the magnification is equal to 1, it's the same size. And if the magnification is less than 1, it's smaller. So,
Okay.
yeah. So, like, that's because magnification has this negative sign in front of it. And we know from this over here that if something is uh if the image is down, meaning if it's inverted, it's negative. So if something is going to be a negative, oh sorry, if we plug in a negative value for for I, it will be negative of a negative, which will be positive. And so that will be, yeah, that. And then the the same thing or opposite for with if the magnification is less than 100. So yeah, you could, I guess, just take like a screenshot. That would probably work. Um,
I can just
yeah.
export it again. That's fine.
Mhm.
Okay. Got it.
Okay, cool. So, all right, here, close that, and then you can show me some questions.
Um, can you see my screen?
Mhm. Oh, this is
Okay.
exactly what we talked about
Mm-hmm. Yep.
with myopia and stuff.
Yes.
So we don't even need this passage for this question, right? Because we know from what I showed you that it would have to we would get rid of which choices.
Um, well, we would get rid of C and D.
Yep. So we get rid of converging, good. And then from what I showed you also, diverging always SUV, right?
Yeah.
So
That's true.
A says real inverted, which won't be true, right? So B, right?
Yeah.
Yep.
Um, should we do the passage or should we do the questions?
Let's see. So,
This one is more reflection refractions. So is this one.
oh, okay. There's also that thing. Do you
Mhm.
do you understand like Snell's law and stuff?
Um, I haven't like
Uh-huh.
honestly reviewed it much, but
All right.
I I can try to like let me see. And you can correct me if I'm wrong. Like here you have like an index of refraction of like one medium and the other. And so this is theta 1 and theta 2 is like it says it there, but like the angle of the incidence light and the angle of the refracted light, and there's like a normal that we can um think of it, and we can think of like if it's going from like uh it medium that has a higher index of refraction or lower index of refraction, it will bend more or less
All right.
away from the
Yeah.
normal. Yeah.
Let's go back to that whiteboard for a sec. I can go over this in that like really quickly.
Yeah, sounds good.
Yeah.
Yeah, should I stop share? Yeah.
Mhm. Okay, so I'll draw it here. Um, so first of all, in index of refraction is equal to C over V. So tell me what's C?
The speed of light
Um
in air.
uh um so what do you okay, so for let's say sound, right? Tell me like in terms of less than greater than for sound, like I'll even write it. Um let's say in a solid compared to a liquid compared to a gas.
Yeah. So solid is fastest, then liquid and then gas.
Mm-hmm. Good. What about vacuum?
There would be no sound.
Correct. So sound benefits from going through a medium and the denser that medium is, right? Okay. So C is speed of light in a vacuum, which is the fastest it can travel.
Okay.
And V here is the speed of light in a medium. And it'll be whatever that medium is. So we can see that um so so V would be less than C, right?
Yes.
Or we could say like if V is equal to C, N is equal to 1, right?
Yeah.
Um now the slower it gets in the medium, the larger the N value is, right?
Yes.
So yeah, so we can say N is proportional to the V. So the higher the N value, oh no, sorry, N is inversely proportional to the V. So the higher the um the higher the index of refraction, the N value, the slower that thing travels in it, right? Okay, so now let's say this is N is equal to or maybe I'll just write, let's say N1, N2, and N1 is less than N2. So I'm going to draw light entering in to a more dense medium. So let's say this is the ray for light here. So this will be theta I. What do you think that I is for?
Instance.
Good. Now usually you won't see this, but like you'll also have reflection happening. And for that, I'm going to use lowercase r. Angle, oops, of reflection. And these will be equal pretty much mostly all the time. All right. Angle of incidence is equal to angle of reflection. Okay. Now, as light goes through to the next medium, it's going to start to bend, and that's what we call refraction. And if it's going into a more dense medium, it can it can bend either towards the normal. Oh, and the normal is just this vertical red line that I drew.
Mhm.
So it can go towards the normal or away from the normal, or it can go same angle. What do you think it would be?
If it's, what's the question? If it's bigger?
Oh yeah. So what would the refracted ray that goes into N2, would it bend towards the normal, away from the normal, or it'll be the same as the incident?
What's like the refractive index of the,
Oh,
I think I need to know that,
so N2
right?
is larger than N1.
And two is larger than N1. Um, um, I think it'll bend. Well, I don't know. I guess right now I'm taking a 50-50 guess. Um, uh, I'll say towards the normal.
Mm-hmm.
Okay.
So something like that. And I'll use a capital R for that. And this would be like the angle of incidence would be larger than the angle of refraction, right? Because if it bends
Distance.
towards the normal, the angle will be smaller,
Yes.
the
Instance.
incident angle. So, okay, so that's that for entering into a denser medium. But now, what about, let's say, N1, N2, but let's say now N1 is larger than N2.
Okay. Then it would be bending away from the normal.
Mm-hmm. So we would have, say, oops, like this. So now let's say this is angle of incidence, angle of refraction. So now the angle of, oh, sorry. The angle is measured from the normal. So now the angle of incidence would be less than the angle of refraction, right? Okay. Now let's see. So it seems like let's say we increase the angle of incidence, the angle of refraction should increase too, right? Like if I were to increase this way, this would increase that way, right?
Yeah.
So let's say we do that until the angle of refraction is 90 degrees. So let's say that we took this blue one here, and let's say we have it there. And then let's say that we do it until the refracted ray is right there along that interface. So I'll write so as this increases, this increases too. But when the angle of refraction is 90 degrees, the angle of incidence is called this, the critical angle. Okay? The critical angle is the angle, like, is the angle of incidence that produces a 90-degree angle of refraction. Okay? So you can also see this as 100% refraction, 0% reflection. Okay. Now let's imagine if we go beyond that. Let's say like this green arrow here. So as we go beyond that, whoops, this angle of incidence now will go beyond that 90-degree part. So it'll look kind of like this. So now we don't really have any of this light coming in into that's trying to get into N2. None of it gets into N2 because it's all being reflected back into N1.
Okay.
So when the angle of incidence is larger than the critical angle, right? You get 0% refraction and 100% reflection. And this is called TIR, total internal reflection. Now, have you ever seen
Like the fiber optic cables? I think
yeah,
that's usually
yeah. What do you think I was gonna say about that?
that they use total internal reflection to like to propagate a signal.
Yeah, so like here's like an example of some fiber optic cables, and you can see the light, it's not leaving the sides, it's just leaving at the end. And here's like a diagram for it. So it just bounces around inside. So like certain like internet service providers offer fiber optics, And, think about, I guess, what you would have if you didn't have fiber optics. You would just have a regular, like copper kind of cable. And remember when we talked about that, as electrons travel through, they experience resistance, right? But for this fiber optics, we don't have like copper atoms that that electrons are brushing across, causing friction. We just have light that's bouncing around in there. And you get to transmit data super, super, super fast.
Yeah.
So, yep. So that's basically all of that. And then, yeah, when it comes to Snell's law, like, um, let's say angle one sine, oof, um, let's say like sine, like n1 sine one is equal to n2 sine two, right? If let's say angle one is equal to the critical angle, angle two is equal to 90 degrees, but sine of 90 degrees is one. So when you have the critical angle, right, it would just be n1 sine theta 1 is equal to n2, right?
Yeah.
And yeah, so the Snell's law thing can make sense from there. But yeah, essentially what we have here then is if you're going from a less dense medium to a more dense medium, the angle of refraction will be smaller than the angle of reflection, than the angle of incidence because it bends towards the normal. And that's pretty much all there is to that. But if you go from a less dense medium to, sorry, you go from a more dense medium to a less dense medium, it'll be the opposite. It'll bend away from the normal. And if you just imagine that going as far as it can go, like to 90 degrees bending, that angle of incidence is the critical angle. And if you go beyond that critical angle, it'll start to reflect.
Okay. Yeah. This is helpful.
Yeah. So yeah, you can do another export. All right, got it.
Yeah. Got it.
All right, you can show me the question again. All right.
Mhm.
So okay, they give us the incident angle, right? And they give us um the refraction, the angle of refraction, right? And we see that the
Yes.
angle of refraction is smaller than the angle of reflection, right?
Um,
Oh, wait a sec.
incident light, fixed
Hold on.
refraction.
This angle, the way that they drew it seems to be sideways or something.
Here.
Yeah. So, okay.
Yeah. I don't know. Oh,
It,
I guess it's the same if you flip it.
yeah. So, okay. I guess like we could still do this. Okay. So let's go back up. So, okay. So like we basically have then, okay. So angle of incidence is 50 degrees. Angle of refraction is 35 degrees. So we see that it's bending towards the normal, right?
Yes.
So that means
Which,
that, yeah.
if it bends towards the normal, it means it's going into a denser medium,
Mm-hmm.
which means a higher
And,
index of refraction.
mm-hmm. Yeah. So, okay, they're talking about the camera lens's refractive index. So we would need to use the passage to see if that's talking about if it's talk like if that's the like where is it coming from like the air or wait, let's see. The camera lens, yeah, I'm trying to see if the camera lens is the more dense medium or the less dense medium.
Yeah.
Okay, let me see. Okay, so flash photograph off the retina captured by the lens. So I guess it's going from the air to the lens. So the lens is going to be the more dense medium here. So we need to find, so like we'll have N1 sine of incident angle is equal to N2 sine of the whoops, sine uh, of the angle of refraction, and N2 is what we're looking for. So N2 would be N1 sine of 50 over 30 sine of 35 degrees. And I guess if they told you something that would mean that N1 is equal to 1, then that N1 value would just be 1, and so that'll be the sine 50 over sine of 35.
Yeah.
Let me just see where it tells you. Okay, so they're saying in the given scenario, the incident air ray in air N1 of N1 is equal to 1. So yeah, I guess so air is the original location. Um and the lens is a new medium.
Is it always one? I think it is in air
That's
or
weird because I mean usually I see it's I mean it can't really be 1. It's gonna be like 1 point something. Uh but it seems like they didn't really like tell you that, right? Or did they tell you anything about that?
no, they didn't.
Okay. So I guess, well, the other choices have just straight up 1, which is going to be the case, if you don't have uh like if you have like let's say total internal reflection. So yeah, I guess we can just consider the air to be 1 in this case. But all in all, you should be getting this, right?
Yeah.
So B is out, and C and D have to be out as well, right?
Yeah.
So like the C and D, like with the 1, that'll be if the angle of refraction was like, sorry, would be like if you had um critical angle, right? Where one of them would be sine of 90, which is 1. So C and D would be if you had something like that. So yeah, so this one will be A. Yeah. I think we're going over a bit, but let's see if maybe we can do one more. Let's see. Oh, okay. So there's something called diopter. So the um 1 over F in meters, I think that will be
Yeah, I think that is a diopter. Or like a diopter would be uh like a meter to the -1
yep.
because of this. Mhm.
Yeah. So like yeah. So yeah, okay.
Yeah. Yeah, and then there's this other thing that was confusing to me
Mhm.
is lens strength. So lens strength is also one to the F.
Yeah, because
Yeah.
like, when you get your contacts probably have something like this.
Yeah.
So and that's in diopters. So
Yep.
mhm.
Think, an option is focal distance two focal lengths. Okay.
Yep.
Yeah, this one was tricky to me. Um,
But yeah,
because they asked for the ratio. Um, I can just it was something to do with triangles. And because it's located at two focal lengths from the center of a converging lens. Um,
I mean,
yeah,
that's a way to do it if you didn't have that table known,
yeah,
right? But even if you didn't have the table, you would still be able to solve this by equating the object to 2f. But we know that when the object is at 2f, right, the image is at 2f, right? And that would
yes,
be a same size image because like the ratio of the height of the image to the height of the object would be, well, the same, right?
yes.
So
I really have to memorize that table.
yeah, yeah, yeah,
Yeah.
yeah. I even like would write it down in like the first 15 minutes before your test
Yeah.
starts.
I had a question about that. Like, do you recommend like doing that with the formulas?
Yeah, with
Um,
whatever is in like whatever's in your short-term memory that you're not confident is in your long-term memory, like I would just do a brain dump like on the sheet. Like I remember going to the test and on my way there just blasting through as much Anki as possible. And then I go to the test and you have 15 minutes to do the tutorial, which never takes that long. So I would just brain dump like optics table, like whatever you feel like is good to do a brain dump on that you're not going to remember afterwards. I would start with this. I would start with tiny UV, SUV, SSUV, LIR, LUV, and I would go from there. So, uh,
yeah,
and also know that SUV, like same size, would mean they're both image distance and object distance are both 2f, and then I would branch out from there.
I see.
Oh, and then also you know that as you go down to get larger images, object distance goes down, image distance goes up.
Yes,
So that can help. But yeah, so this will be this. Mhm.
yes. The last one was another
Okay.
strength question,
Yep. So
but it
there.
was -4. Yeah,
Uh-huh. Oh wait, they're saying eye lens now. So that's like the cornea. Okay, so that's that. Okay, all right. So this is going to be a combined. Well, I was going to say you could treat it as a compound, like multi-lens system, but apparently for multiple strengths, you just add them based
yeah,
on what we see here. So that's even easier. But there could be questions where you have a multi-lens system, and that's why I put in that exception for the upright. Because like if you have an upright image here and you create a inverted real image here, that a real image could be treated as an object for this new lens, right? And it will produce a real image that's upright. So that's why when I
mhm,
wrote like when I say the U and the I, like think of it as inverting, right? Because we have an upright image here, inverted here, which is what happens when you create a real image. And then if you take this inverted real image as an object and we create an inverted real image of that, we're inverting what's inverted. So then this real image becomes upright.
upright. I see. I
That's
see.
the exception.
Like an inversion of an inversion kind of thing.
Yeah, yeah, exactly.
Yeah.
Yeah. So that's why even though I say upright and inverted, I would say like inverting, like a verb.
Okay.
So that's the exception.
All right.
So yeah, that should be enough for you to try all these optics questions. And yeah, that should be it. I mean, they can be. I'm trying to think of like Yeah, there'll probably be like a couple that will be a lot harder with some other stuff, but this should be enough for mostly all of this. Yeah.
Okay, sounds good.
Hmm.
Um, yeah, I'll stop share now. Um, yeah, I guess we can this weekend, I'll be taking a test. And you said we were, I
Yeah.
think, I don't, yeah,
So yeah, I was gonna decide by today. So that I think when we met on Monday, that's when you were like really tired. So I would have thought differently then. But since then, it seems like you're doing well. You're like on top of all this. So I would say to do another blueprint test. Um, but what do you think? Maybe what I'm registering uh is misleading. What do you think?
I don't know. I feel like I would like to have a better idea of like where I am. But that won't really make a difference at the end of the day. So I maybe I should just do the blueprint. Um,
Did you run out
yeah.
of cars, Jack Weston cars stuff?
No, I've only done one.
Oh, what did you do for? Because we've done three. So that first one you did
I,
car feedback.
the first two I did the question packs from the AMC.
And the latest one was the Jack Weston.
Yes.
Okay. The score seems to be roughly the same. So yeah, I would say to do another blueprint. And yeah, I think and in car for cars do another Jack Weston cars, and then we'll have another score that will roughly be similar to how you've been doing. Um, and then after that you'll be doing like an AMC one. So yeah, I would say to do another blueprint, like your last blueprint essentially, and use a Jack Weston cars. Uh,
Okay.
yeah, that's what I would say.
Um, yeah, I guess I think the one I haven't done ever would be like Blueprint 5, so I'd probably do that.
Mhm.
Yeah.
Yeah. Because for the AMC ones, I think you like what there was like you did all of them, I think, or no.
I've done all of them last year.
Oh, okay, okay. Got it. Yeah. So since you did all of them, and I think you were getting like a 517 or something like that, or like uh I just wrote like AMC full lengths 517, but that was probably just on one.
Yeah, that was one.
But yeah, just because you did them all, like that's why, and you got high scores like that. I think yeah, we should do another blueprint one. Um, and then you can do like an AMC one, the week after. Uh, yeah. What do you feel like?
It's good. Um, and well, I guess I'll have yeah. So I know a lot of people recommend doing the section banks at this point as
Oh,
well.
forgot
Um,
about that.
which
Did you ever?
which I've done them before, but like maybe it would be a good idea for me to redo them.
Uh-huh.
I don't know. Or UWorld, I don't know.
I would say UWorld. Just because you've done them before, and also like it's not just that you've done them before. I think that your because what I wrote also was like a 501, I think, for like the blueprint tests, or maybe you just did one. Like when we first met, I wrote
Mhm.
501, I think. That was just for one blueprint test, was it? Or
I think my first test.
okay. So like if like it's just one test, so I can't be conclusive in saying this, but if a 501 blueprint translates to a 517 AMC, 511, 509 blueprint should, translate to pretty high AMC test score. So I think that, yeah, so I think that continuing to do questions that are both hard and that you haven't seen before, like let's do that for like, you know, just like one more time, and then we can move on to like the easier ones. Because yeah, like while I don't want you to be like discouraged and stuff, I want you to have like a more predictive result at the end of everything. Um so yeah, I would say to do that blueprint full length 5, do one of the Jack Wesson cars tests, and then we'll review it together and stuff. But basically like this weekend, and then like some like maybe like up to like Wednesday or something next week, we'll be done with blueprint stuff. And you'll be able to take your AMC full length like next weekend. And then I guess during the week we can have you, all right, so during the week we can have you do more UWorld, and then maybe like after your AMC test, like the week of, like I don't want you to do anything like the day before, but like maybe like the week of, you can, if we
Right.
if it seems to be a good idea at the time, we can have you do like the section bank again.
Okay. I don't know if I told you this, but I took that week off, the week of my
Okay.
test,
Got it.
of work.
Mhm. All right, awesome. Yeah, so that's what I would say. I'd say go with the blueprint, Jack Weston cars, and then we'll go over some stuff from that next week, and then some UWorld stuff, and then you'll take your AMC test, and then after that could be like section bank stuff. So,
Okay,
yep.
sounds good. So we'll reconvene Monday, and I'll email you how it goes this weekend.
Yep. Awesome. So yeah, good luck, have a good weekend, and I will see you like on Monday. Okay.
All right, sounds good.
Great.
Bye.
Take care. See ya.